Suppose we want to measure the velocities of the atoms of a gas or vapor in a box at a temperature T. Here's the apparatus that we'll use. On the left is a box or oven for vaporizing potassium. Actually, I can't measure the velocity of the atoms in the box. I have to let them out so that they form a beam. When a slit in this rotating drum is here, some of them can strike a detector. The moving slit chops the beam, and I can measure the time it takes a burst of atoms to get to the detector. Of course, all this occurs in a vacuum. Now let's look at the details of the apparatus. Here's our oven. I put potassium in here. The atoms come out this slit and go through the slit in the drum and across to the detector. The speed of the drum and the width of the slit determine the duration of the burst of atoms. I can change the time of flight of the burst of atoms by moving the detector. Now let's remove it and take a closer look. I'll take off this shield. The neutral atoms go through this grid and strike this tungsten wire that you see here. The wire is heated by a current passing through these leads and is kept under tension by this spring. The neutral atoms are ionized when they strike the wire, and the ions are collected by the grid. The current is let out, amplified, and displayed on a cathode ray oscilloscope. Diametrically opposite the drum slit is a mirror. It's used to reflect a beam of light into this photocell. We drive the drum by means of a magnetic coupling. The beam of light flashing back to the photocell triggers the scope sweep. Sometime after the start of each sweep, a burst of atoms striking the detector produces a pulse when a beam is present. Between the drum and the oven, there's a baffle. It fits closely inside the bell jar. This baffle keeps stray potassium atoms from getting into the detector. I'll remove the oven from its heater. When the potassium is heated, it fills this box with vapor. Here's the oven slit. The oven is closed by this lid, which has a thermocouple calibrated so that this meter reads full scale when the oven is 400 centigrade degrees above room temperature. Here's the potassium being put in the oven. These are the thermocouple leads. It takes several hours for the apparatus to pump down and the oven to heat up. We're all set. I'll open the beam shutter. And there's our beam. The atoms, about 50 bursts per second, make these pulses, which are spread out in time because they have different velocities and take different times to travel from the drum slit to the detector. The detector is now about 2.5 centimeters from the drum slit, which is as close as it'll go. I'll make a still picture of this pulse and then move the detector back, stopping for a picture every 2 centimeters or so. Notice that the pulses are changing in height and in width and in position. But I expect to get the same velocity distribution from each of them. Now the detector is back as far as it'll go. Here are enlarged time exposures where there are 10 or 20 traces of the scope sweep. L is the distance between the drum slit and the detector. This time is the time between when the slits line up and when the peak of the pulse occurs. We notice that as we move the detector further from the source, the pulse gets wider and the position of the maximum moves towards later time. Now, if there were only one velocity, we could get it directly from these pictures. We need only to divide the length L by the time of the maximum. From the geometry of the apparatus and from data taken at very low drum speed, I know the width of the pulse if there were only one velocity. It would be about 7 microseconds. That's about the width of this crayon mark. So all this extra width must come from the presence of many different velocities. Here's why. The drum is turning, and the sweep starts when the slits line up. Suppose there were a detector right here. Then I would get a burst of atoms which would give a pulse that looks something like this. It, of course, is made up of a certain number of fast atoms, medium velocity atoms, and the rest in here might be slower atoms, all piled up together. Now suppose the detector is back here. When the drum turns and the slits line up, the sweep starts as before, and nothing happens for a while. Then the fast atoms start coming in here. A little while later, medium speed atoms, and then the slow atoms sort of fill in here. This is how the pulse which we see is formed. Actually, these pulses overlap, which I can neglect, because each of them is only 7 microseconds wide. Whereas the whole pulse in this first picture is actually 100 microseconds wide. Here's a sketch of the pulse. I've divided it into 10 time intervals. Let's consider the time interval between t equals 2 and t equals 3. If the distance between the drum slit and the detector slit is 12 units, then all the atoms in that time interval must have velocities lying between 12 over 3 and 12 over 2, 4 and 6. So if I want to draw a velocity distribution, those atoms in this time interval will appear down here. Now I'll draw them in, something like this, between 4 and 6. Consider the next interval, from t equals 3 to t equals 4. Those atoms will have velocities between 4 and 3 and will appear here. Now this velocity interval is half as big as this one. But there are more atoms coming in this time interval. So I must draw this rectangle more than twice as high as this one, in such a way that this area is to this one as this area is to this. The next interval, from 4 to 5, will have atoms with velocities between 2.4 and 3, and so they'll show up something like this. And now you see, I will be drawing skinnier and skinnier rectangles that represent the slow atoms arriving at later and later times. The fast atoms come in out here and make a sort of tail like this. Now I can draw in my velocity distribution. I can make it easier to fit it if I use more time intervals, but that's tedious, and I can avoid it by using the following procedure. If I plot velocity against time, I get a hyperbola like this. And if I have constant time intervals, delta t, then for a short time I'll get velocity intervals of moderate size. As the time gets longer, the velocity intervals get smaller. I can express this way. Delta v equals minus L over t squared, delta t. So to get the right area in proportion on the velocity distribution, I must multiply the height of this curve, the pulse, by t squared before plotting it on the velocity distribution, simply to compensate for the fact that the width of the velocity interval is getting smaller with t squared. Here is the velocity distribution in the beam obtained from all 4 pictures. I've plotted velocities along the abscissa, and along the ordinate, the relative number of atoms per unit velocity interval. The different pictures are identified by circles, squares, and triangles. The peak of this curve is the most probable velocity in the beam, 62,000 centimeters per second, and that corresponds to a temperature in the oven of 590 degrees Kelvin, which agrees pretty well with the measured oven temperature. This is a plot derived from kinetic theory of the velocity distribution in a beam of potassium atoms from an oven at 590 degrees Kelvin. This differs from the Maxwell distribution of velocities because we measure the flux of atoms in a beam and not the density in a box.